Hello again everyone, welcome back to ptet.chemistry channel. In this tutorial video, I'll continue this section B topical MCQs on topic 5, which is on chemical energetics to do with enthalpy changes, exothermic, endothermic reactions, calorimetry, bond energy calculations, all that sort. Yeah? So the four options that we know in this section B kind of MCQs are divided into these A, B, C, D, where 1, 2, and 3 relevant to what they're asking is option A, 1 and 2 is B, 2 and 3 is C, and if only 1 is relevant to whatever they're asking, that's option D. So in this first question, we have hydrazine. Hydrazine is a molecule that looks like this, that you will have known from your structure and bonding as a relation, as a very close relation to ammonia. So it's got, it looks like ammonia, but instead of 3 hydrogen, it's got nitrogen bonded to another nitrogen, such that you have NH2 on each part. And what's interesting is that you get a 107.5, or you can call it 107 degree. I usually leave it at 107 degree, but it depends on what you really like. 107.5, perfectly acceptable for trigonal pyramidal geometry with 3 bond pair and 1 lone pair on each nitrogen, and then you talk about valence shell electron pair repulsion. This question is not about structure and bonding, it's about its exothermicity. So this reaction releases heat when you combust hydrazine. That's why you use it as rocket fuel, and then it combusts to give you nitrogen gas and also H2O, therefore there's no carbon dioxide being given off. However, hydrazine does not spontaneously burn with oxygen despite all these good things that come with it. Why does it not burn spontaneously? That means even if you put oxygen to it, in the presence of oxygen, it doesn't go straight away, okay? And it's got nothing to do with the nitrogen-nitrogen triple bond, because you are not reacting nitrogen-nitrogen triple bond. You have N single bond in N2H4. So this is the different scenario. And then N and N, there's your N2, is a product in this reaction. It is not a reactant. So you do not need to break this bond in the nitrogen molecule before you can react, because you are producing this. And I guess it's back to the structure and bonding. It's a single bond. It's not a triple bond, because if you start drawing this thing, which is wrong, if you start drawing this thing is wrong, because that will give nitrogen with 1, 2, 3, 4, 5. This is not accepted, because your nitrogen would have 10 valence electrons. Well, if you count the one that are involved in covalent bonding, if you use all 5 for covalent bonding, you will have 1, 2, 3, 4, 5 covalent bond, 10 valence, 10 electrons in the outermost shells. Your nitrogen is only, each nitrogen atom is 1s2, 2s2, 2p3. When you are in n equal to 2, second shell, you can only fill in the 2s and the 2p. There's a maximum of 2, there's a maximum of 6, 2 plus 6, maximum 8 electron in the outer shell. 2 is definitely wrong, because this structure is definitely wrong, and therefore only 1 is correct. Okay, so hydrazine is indeed a liquid at room temperature and pressure, but this does not explain why it does not burn spontaneously, so always relate to whatever they're asking you. In this next question, we have carbon monoxide burns readily. So in the previous question, hydrazine does not burn readily, does not burn spontaneously, but carbon monoxide burns readily in oxygen to give you CO2 gas, like this. And I have to balance my equation. What can be deduced from this information? So I wrote a balance equation already. So if you have this reaction that you want, and then we say, if we have enthalpy change of formation, if I'm given the enthalpy change of formation, if I let this be x, let this be y, this will be 0, because it's an element. So you form an element from its element. That's why all elements in their standard state have 0 enthalpy of formation. So knowing the enthalpy of formation, we know that it's the sum of the formation of products minus the sum of formation of the reactants that will give you the enthalpy change. So we also know that there will be there will be y, and there will be y multiplied by 1, and then minus X multiplied by 1 as well, because you are forming 1 mole of CO2, so 1 times that. You are reacting 1 mole of CO, so 1 times that. So y minus x equal to delta HR. And what do we know about this? They say that it burns readily in oxygen. So actually, that is something that you will learn more in A2. This is to do with Gibbs free energy. Although most reactions that happens readily would imply, okay, I'm not saying always, but it would imply that enthalpy of reaction is exothermic. So most exothermic reactions would be feasible and spontaneous and readily happen, because that would imply that delta G is lesser than 0. This is something that you will learn more in A2 energetics. So if we think about that information, which is not very directly given in this question, if we think about that, that is lesser than 0, so the delta H is lesser than 0. So if delta HR is less than 0, so y minus x is lesser than 0, so y is lesser than x. Going back to statement 2, the formation of CO2, which is y, is more negative than carbon monoxide. Y has a smaller value, so y is more negative than carbon monoxide. So if that is more negative than this, then your overall will be negative. So this is correct. Statement 2 is correct. That means if y is more negative and x is less negative, or x is more positive than y, this inequality satisfies the condition, right? How about number 1? The plus 4 oxidation state is more stable than plus 2. If we work out the oxidation state here, the carbon is plus 4 because each oxygen is minus 2. The oxygen is minus 2, therefore you get carbon plus 2. The fact that you readily form CO2 means you really want to go to carbon plus 4. So that means the carbon plus 4 is more stable than the plus 2. That's why the reaction happens readily. Okay. And then if we think about the equilibrium constant, so assuming it is an equilibrium, that's what this question has implied, it's likely to be high. If you burn readily to give you carbon dioxide, this reaction will favor the formation of CO2, and therefore this will give you the reaction favoring the forward reactions, and therefore the equilibrium constant is likely to be high because it will favor the forward reactions. So all three of them are correct. In this next question, so we want the reactions where the enthalpy change represent both a standard enthalpy of combustion and the formation. All right, so I can tell you the one thing you should be looking for is statement 2. This is forming 2 mole of the substance. Forming 2 mole of the substance already contradicts formation, because enthalpy change of formation is defined for forming 1 mole of the substance. 2 is incorrect. You're left with option 1. If you think about option 1, you are forming 1 mole of the substance from its element, all of them in their standard states under standard conditions, so formation is okay. Combustion, if you think about the combustion, enthalpy of combustion of carbon is defined as burning 1 mole of the substance, 1 mole of substance in excess oxygen, okay, all of them in their standard states, including the products, under standard conditions. So the combustion of carbon is equal to the formation of CO2. This is one of the most common relationship that you'll be able to deduce if you have revised your chemical energetics properly. The next bit, it already contradicts formation because of this thing. You are forming 1 mole of the substance, yes, but not from its element. CO is a compound, CO is not an element. Okay, so not element. So that's why the answer must be D. Next question. So this is an energy profile diagram. We are going to be thinking about forward and backward reaction. So if you have reactants going to products, that is forward, and then product going to reactant, that is backward. Alright, enthalpy change of this reaction is going to be from the energy of the reactant to the energy of the product. So from the energy of the reactant to the energy of the product. So it's a one-way thing. So it's X. So that is X. So that is the blue one. And then activation energy for the blue one, activation energy. So the blue one refers to forward reaction. Okay, so W is the activation energy for the forward reaction from the start to the top of the hump, to the top of the peak, from the reactant to the energy of the product, so one-way direction. So that is the enthalpy change of the forward reaction. If I use a different color, this is for the backward reaction. So that is the activation energy for the backward reaction, and this is the enthalpy change for the backward reaction, because the product gained this much energy to become the energy level of the reactants. The products need to get this sufficient amount of energy to reach the top of the hump. Okay. So what do the labels in the diagram represent? Based on what I said, if you think about Z, Z is the enthalpy change of the backward reaction. So first bit is correct. And then Y is equal to the activation energy of the backward reaction. Y is that, so that is correct. If you look at number 1, enthalpy change of forward reaction is going to be X. So it said W is the enthalpy change of forward reaction. That is incorrect. W is equal to the activation energy of forward reaction. So number 2 is correct, number 1 is wrong. You can only be left with option C, which is 2 and 3 are correct. Okay, X is equal to the enthalpy change of forward reaction from the start to the end. Okay, so that is X being enthalpy change of forward reaction. Activation energy of forward reaction is from the reactants to the top of the peak, so that is W. So in fact that is correct as well. This is the last question of this 5-question series on chemical energetics. This is more energy profile diagram. We're going to be thinking about forward and backward reaction again. So reactant going to product, product going to reactant. Always specify your forward and backward so that you are never ever confused. So this is your backward, let's say, and this is your forward. So if I draw it, this will be your I should probably use a different color. If I draw it, this is activation energy of the forward reaction. This is your enthalpy change for the forward reaction. If I use a pink color one for the backward, this is your activation energy of your backward reaction. And this is your product, this is your reactant. So going this way, that way, going upward, that is your enthalpy change of the backward reaction from your product to your reactants. Okay, so enthalpy change for the forward reaction, as I mentioned, is going downward, so it's minus 30. That is correct. Forward minus 30. Forward reaction is exothermic, yes, because going from reactant to product, your product have lesser energy than the reactants. Your enthalpy change goes downward. And then for the backward reaction, enthalpy change for backward reaction is from here to here, so that is just plus 30 and it's not plus 90. Okay, so that is wrong. It should be plus 30. This could very well be your theory level questions where they say state the value of the activation energy of backward reaction, for example, and explain why, something like that, right? Okay, so it's very important that you can do these kind of simple things. So this is it for this 5-question series. Click the button on the bottom right, subscribe to the channel if you have benefited from these tutorial videos, and share the channel with your friends, your classmates, your class group chats, and anyone else really you think might help, might need the help with chemistry. So thank you for sharing and thank you for watching. See you in the next video.